Ni hao. Let's talk about Schottky diodes. So this, within the scope of the devices we're looking at, the PN diode, we have looked at large signal, and in the past we just looked at small signal devices. Today we're going to look at yet another diode. It's the Schottky diode. It's a metal on semiconductor contact. It has a slightly different circuit symbol. It has a little squiggle on the end. We're going to look at, of course, at the equilibrium band edge diagrams at first, and then look at DC, and then expand into small signal and large signal device performance. And you'll see this is a pretty special device. It's a majority carry device, so we can handle small signal and large signal combined. All right, so here's the outline of this section. We'll talk some basics, band edge diagrams, and a simple current derivation, and then we'll look at physical processes, and then some very practical issues for these Schottky diodes. All right, physically we have a metal on N-type semiconductor. That's a typical M-S Diode, and we typically just use the one-dimensional representation where we consider a sliver. And you might see symbols like this, and in the textbook you have a representation that looks like this. So let's look at some applications real quick. So the first metal semiconductor or Schottky diodes were really the whisker detectors, cat whiskers, or the original bipolar transistor had these contacts in it. If you are studying carbon nanotubes for transistor action, you'll need to deal with Schottky contacts there as well. And of course, if you are into STM microscopy, where you have metal tips that are sort of getting lowered into surfaces to measure surface details, etc., you certainly deal with a Schottky contact as well. So these are typical historical applications, but this thing has a really important application even today, because all our MOS devices have these contacts in them. All right, so we'll start with a band edge diagram, of course, in equilibrium. And I just want to remind you that a metal and a semiconductor are somewhat different. In a semiconductor here, in the N-type doped semiconductor, we have the Fermi level close to the conduction band edge, and we manage somehow to populate a few states here in the conduction band, versus a metal really has a Fermi level roughly through the middle of a band. There's a ton of density of states. There's a ton of carriers. The number of carriers you have at the Fermi level for a metal is vastly, vastly larger than what you have in a doped semiconductor. So you need to keep that in mind for the next few pages. So here we go. We're going to start drawing an band edge diagram. We start out from equilibrium, of course, and draw a flat Fermi level. Now we're going to draw the conduction and the valence band in a metal. So I just stated that the conduction band is below the Fermi levels in a metal, so the valence band is even lower. And we'll draw a vacuum level in the metal. That's the energy needed to take out an electron. We'll have a metal work function like this that is measuring the energy from the Fermi level to the vacuum. For the semiconductor, we do the same thing. We've done this now multiple times, where we draw the conduction band and the valence band, and we draw in the vacuum level in the semiconductor. All right, let's do so. Now, in terms of overall energy scale, the vacuum level is the one that is continuous throughout the device, meaning we can connect this level across the heterostructure. And that's the true energy level in the system that is a constant. So we need to keep that as a reference. We translate that reference down to in the metal heterostructure for the conduction band and the valence band, and we do the same thing for the semiconductor as well. So for the conduction and the valence band as well. And what you see is something that you might not have seen as such before. There's a heterostructure. There is now a sort of a kink in this band edge diagram that is not quite as continuous as you had seen it in other diodes. So this is a heterostructure, a metal to semiconductor heterostructure, and the band edge is looking quite different. All right. What is the same is that, again, the dielectric displacement field needs to be continuous, which results in this charge neutrality condition here, where the number of exposed donors on the electron side needs to be balanced by the dipole or the charges that are exposed or in addition showing up in the metal. So we do keep in mind again that the density of states in the metal here is much, much larger. Therefore, the number of equivalent donors or available electron states that are available is vastly larger. So therefore, this XP here is going to be significantly smaller, and that's why the band bending that is seen here is mostly happening in the semiconductor, not in the metal. All right, so we do neglect the band bending pretty much here in the metal, and we'll justify that in a minute. Now, there is an introduction here of a concept that is a barrier potential. That's the barrier that is being seen by electrons in the metal that would like to transition into the semiconductor. So they see this phi b for barrier, okay? And then we have this metal work function still here. We mostly worry about this phi b from now on. Now, overall, again, we need to sum up to a constant energy, and that's referenced against the vacuum level. We have a built-in potential, and now we want to figure out what is this built-in potential, okay? So we have from the doping delta here, the energy from the Fermi level up to the conduction band in the semiconductor. We have the affinity to the vacuum level, and we had transitioned the vacuum level all the way around to the metal, and going back down to the Fermi function in the metal work function, we now know what the energy or the built-in potential must be. So it's really now, we can reduce it to the built-in potential being the difference between the barrier energy here and delta. Okay. We can figure out the delta very easily by assuming that we we can figure this out by the doping in the electron side, on the n-dope side. All right. Now, let's look at the assumption of a depletion approximation for the metal and the semiconductor, and let's assume again we just have rectangular distributions, so we kind of neglect the details at the edge of this distribution here, and we'll integrate the charges, right? So as we integrate the charges, we can get to the electric field that is in the device. So, and we figure out that there's a maximum field, and remember that at this interface, the displacement field needs to be continuous, not the electric field. And we integrate the electric fields in the structure and get to the electrostatic potential that we can then translate overall in the device, and we end up here with a built-in potential. Now, given that we know the width or the extension of this depletion region in the doping side, we can figure out what the maximum potential here is in the built-in potential. Now, what we're doing is ultimately we're neglecting this, again, the width of the sheet charge and the metal. All right. So we'll neglect that, and therefore we can neglect the potential drop in the metal. All right. So the assumption is that you have so many carriers there that they can screen any potential really in the device. Okay, now let's go put in some numbers or some concepts here. Why can we neglect this potential drop in the metal, and do the same kind of graph that we've shown here before, as if it's a normal semiconductor junction, and we'll try to figure out how big this XP would be. All right, so by displacement field continuity, we have the charge balance as well in this red area and the blue area. And we can figure out from the integration of the built, from these fields, the built-in potential, and with the expressions for Xn and Xp, we can now have a dependence of the built-in field on the depletion region length. Okay, we've done this before. It's the very same math as what we've seen in the p-n junction. So there's nothing new here. And we have an expression for the built-in potential as a function of the depletion region length. Okay, now we can resolve these distances on the N side and also on the metal side. Now we have an expression here where we have the number of states in the denominator in this expression. Now, if you can assume that the number of states is much, much larger compared to the doping density that you can provide, then this term drops out. So the expression for Xn is going to be independent of the number of states in the metal. The flip side for the distance of Xp in the metal, it now depends as a square of the number of metal states compared to a linear dependence of the donors. And again, the number of states in the metal is orders of magnitude larger than the doping we can provide in the semiconductor. Therefore, this term goes to 0. This is why we can neglect Xp. Okay? And again, it boils down to this diagram on the top left here, where the number of states available for electrons is much, much larger than the number of states available in a semiconductor like this. All right, so we've drawn an equilibrium band diagram, and now we're going to derive a thermionic current in the system. All right, let's do that. So, of course, we'll start out with Gauss's law again, or Poisson equation, and do this under bias. Now, in a sense, our by now well-known semiconductor equations are not so useful right away because they deal really with a system that does not consist of heterostructures. They really deal with smooth electric fields and smooth band edges. And here we have a heterostructure, and we have to treat the current flow through this in a quite a different way. And that way is actually very close to how we're going to treat semiconductor devices in today's devices, where you have electron flow that's ballistic in these devices. So we'll treat it with a theory of thermionic emission, and I'll tell you more about this in the next few slides. All right, so let's start out again with our depletion region widths, and we have already derived the expressions for the length of these depletion regions. And just as a reminder, what we had done and seen at the p-n diode, in forward bias, this distance xn, the distance of the depletion region gets smaller. Okay, so the depletion region gets smaller, and in reverse bias, the opposite is true. The depletion region gets larger. All right, so in terms of band diagrams, it would look something like this. In equilibrium, we had just drawn the band diagram like this. If we now apply a forward bias, we raise up the Fermi level on the electron side, and we're increasing the depletion region here on next to the junction. Decreasing it, I'm sorry. And if we have a reverse bias, we increase the depletion region length quite a bit, and our band diagram looks like this. So these are just sketches of the band diagram where we add to the built-in potential the applied voltage to our quasi-Fermi level, and then calculate from there the depletion region lengths, just like what we've done in a p-n junction. So the theory and the approach is actually very similar to what we have done in the p-n junction in terms of the calculations of depletion regions. All right. So also the interpretations of the IV characteristics and the final results we will obtain are actually very similar to what you see in a p-n junction compared here in this metal semiconductor junction. All right, so we had identified forward and reverse bias characteristics, and they're all in a way very similar to what we have seen before. In forward bias, you inject electrons from the N side over to the other side of the junction. But these are majority carriers you inject into the metal. They will relax rather rapidly. There is no diffusion involved due to the scattering in the metal. Now, in the reverse side, we have just like what we had before. We're trying to inject carriers, but they're being blocked by a barrier. But we can have tunneling effects, so we can have the same breakdown and the same ionization effects as in the p-n junction. But again, this device remains a majority carrier device, so that time response will be rather rapid. Okay, let's look at the current flow concepts here in this device. So we're going to divide the system into two components: current flow in the metal and current flow in the semiconductor. And in particular, we're interested right at this interface at the junction and label our currents metal to semiconductor or semiconductor to metal. Okay? So those are the two different currents we calculate and express in analytical expressions, and we will use that this current must be constant at a couple of places. So in equilibrium, these two current components must be the same. So that's the principle of detailed balance, and we'll use that as well. In forward bias, the barrier that the electrons from the metal see remains the same. Okay? That means the electron flow, metal to semiconductor, remains unchanged, regardless of the forward size of the forward bias, because the barrier remains the same. Now, for the reverse bias, that is also true. In the reverse bias, also here, the current from the metal to the semiconductor remains unchanged. And that is something we're going to consider and quite useful in the derivation of some equations for current flow in this metal semiconductor junction. So, take-home message here is that the metal to semiconductor electron flow is independent of bias, regardless of the bias that you apply on the semiconductor side. All right. Now, for the electrons coming in from the semiconductor and being injected in the metal, that is different. So for the electrons, the barrier of flow from right to left in this graph is going to be lowered. So there's going to be more thermionic carriers available to transition across that barrier, and electron flow will increase. And similarly, at reverse bias, the barrier becomes bigger for the electrons, and electron flow will be dramatically reduced in this direction. And that is really how you have diode-like characteristics, and that in forward and reverse bias, you have rather dramatic different carrier actions. All right, so now let's look at the left boundary condition on this device. And we'll just say again that there is EC is not continuous, and that there is no minority carriers. It's metal, and it's all majority carriers. And we're trying to inject those into the semiconductor. All right, so at zero bias, when the applied bias VA is 0, the electron flow at this site, at the junction, is the same going left and going right. We'll take that as an important entry into our calculation. That means that the electron flow here in this expression those two expressions are the same, okay? And at 0, they balance out to be 0. Left to right and right to left must be counteracting to each other in detailed balance. All right, now let's carry this further. We are interested in the current from at the junction, and we have at applied bias the current element from metal to semiconductor at applied bias minus the current flow from semiconductor to metal must be the same as just substituting in the metal to semiconductor flow at 0 bias minus the one at applied bias, right? The metal to semiconductor electron flow remains independent of bias. Okay, that means now we can also just express the current expression only in terms of semiconductor to metal. We know that this term here must be equivalent, and now we have a current expression that is solely dependent on semiconductor to metal. And that'll be very helpful because we know already very well how to calculate electron densities, etc. in the semiconductor. And therefore we can calculate current really easily by just looking at the semiconductor and no longer at the metal. All right. Now, in the semiconductor to metal flux, we're considering the following concepts. We're looking first again at the metal charge carrier distribution, okay? And we can roughly figure out how many carriers can make it across this barrier. So we have this barrier with a barrier height theta b, okay? And we have a carrier distribution in the metal. We're assuming that we're in the Boltzmann limit where we're not where the Fermi function can be approximated really by a Boltzmann distribution, and we have a ton of states available. So we multiply the available states by the Fermi distribution of carriers that are available above the barrier, and we are assuming that only half of them go to the left and the other half go to the right. So we're segmenting out the carrier distribution in the metal into a Fermi surface that can go to the left and a Fermi surface that can go to the right, or distribution of carriers that go left and go right. Okay? So and these carriers move at a thermal velocity of carriers in the metal. Okay? So we have, again, charge, number of carriers together times velocity, that's current. Very simple. We've done this now multiple times. Now we look at the semiconductor side. We have a similar distribution, and we figure out how many carriers are propagating above this barrier, okay? And we can write that down again. We have a number of electrons at the surface. We have the built-in potential minus ultimately the applied potential, but right now we're looking at 0 bias. So we have a number of carriers, half of them go left, half of them go right. They have a distribution with a Boltzmann distribution, and they have a thermal velocity of the electrons. At 0 bias, as I stated, these two current components must be the same. Okay. Now, if I apply a voltage on the semiconductor side, all I do is I substitute in addition, the bias in the into the built-in potential. So I lower the barrier and therefore increase the number of carriers that can flow. That sits in an exponential, and that gets me the exponential increase of carriers that can flow across the junction. All right, I'll split that exponential in just two terms as a product, and I identify, oh, look at this. This has the current in it at 0 applied voltage, and it's scaled by an exponential that has the applied voltage in the exponential. That comes in handy because now this must be the same as the metal to semiconductor one at 0 bias. All right. Now I can express everything here as a metal expression with a barrier height that is coming in from the metal. So I have metal properties and semiconductor properties in here. Okay. Now the total current flowing is again as looked in from the metal side as electron flow semiconductor to metal at the different biases. And here's an expression now that I just plugged in like this, okay? And I end up with something that looks rather familiar. This is like the diode we had before multiplied by some coefficient. Okay, so let me compare that to a normal PN diode. I can do the same kind of theory on a normal PN diode as well. So I can leave that to an exercise to you, but if I have no recombination and generation, I can come up with exactly the same type of expression. All right. So the distinction here really is that the Schottky barrier diode is a majority carrier device that has historical importance and is really important still today. There are similarities and differences between PN junction diode for the electrostatics. It is behaving like a one-sided diode, so you consider just the N side in the system, and the metal side is like an extremely heavily doped device where you can neglect any potential drops, etc. And you don't have drift terms in the metal or the semiconductor anymore. The trap-assisted current and the avalanche breakdown and zener tunneling could all be calculated in the same manner, very similar to what we had done in the PN junction, and we'll do that in a little while. So that concludes the section 23.1 on basics, and in the next we'll look into some more details on the physical processes. All right, I'll see you in the next section.